Today we're going to begin our discussion of acids and bases, and we're going to go all the way back to chapter 4 and review acid-base reactions and gas evolution reactions, which are just types of double displacement reactions, which we talked about back in honors chemistry. So an acid-base reaction, also called a neutralization reaction, is when you have an acid that reacts with a base, as you would expect from the name, and the result is a salt and water. So that's just a simple double displacement reaction. So we'll practice a couple of them in just a minute. The hydronium ion is the H plus or H3O plus that you get from the water that reacts with the base. So, like I said, the general format for these is you have an acid plus a base, and the products are water and some sort of salt. So in the examples we have here, we have HCl and NaOH. And just as a refresher, in double displacement reactions, the cations and anions just sort of trade partners in these reactions. So here the H and the OH are going to pair up now, which just gives us water. And then the Na plus and the Cl minus will pair up. And since they have the same, plus 1 and a minus 1, we just need one of each. So our other product is just going to be NaCl as our salt. All right, and the second example we have here, we have H2SO4. So our anion here is SO4 2 minus, and our cation is H plus again. And then we have KOH, and K plus would be our cation, OH minus the anion. So again, one of our products is going to be water, H2O. So if the H plus and the OH minus get together, they make water. And then we have K plus and SO4 2 minus. So we're going to need two Ks to balance out the charge from the SO4 2 minus. So that'll be K2SO4. And then to balance that reaction, or balance the equation, we'll just need two KOHs and two waters to make that balanced. All right, the second type of, and we went over all of these in honors chemistry, so this should all be very familiar, I hope. The second thing we're going to talk about in this section is gas evolution reactions. So in these reactions, a gas forms, as you would expect from the name, and it forms as a result of the reaction between either an acid or a base and another salt. So we're going to go over the 4 examples of these in the next 2 slides. So the first is reaction of sulfides. So in this case, you have an acid that reacts with a sulfide salt. So sulfide is S2 minus. And in every case, when you have an acid that reacts with a salt, you're going to get H2S as one of your products, and then you'll get the salt that results from the spectator ions that are present. So in this particular case here, we have HCl and K2S. So we're going to get H2S as one of our products because the H and the K are going to swap places. And then our other product is going to be KCl. And because H2S is a gas, this reaction results in bubbles or gas evolving. All right, the second one that we're going to talk about, you have all witnessed before. This is this type of reaction that you see when you react baking soda and vinegar. And so baking soda is a carbonate. It's bicarbonate, sodium bicarbonate. And anytime you have a carbonate or bicarbonate that reacts with an acid, you get the formation of CO2. And so the way that happens is first you get carbonic acid, H2CO3, and a salt, and then the carbonic acid breaks down further to make water and carbon dioxide gas. So for this reaction here, for the example, I'll go through both steps, but you wouldn't have to write the in-between step if you just know that you always get water and carbon dioxide. So in this case, our first product is going to be H2CO3, because we'll have the H from the nitric acid reacting or combining with the bicarbonate ion in the sodium bicarbonate. And then our other product is going to be sodium nitrate. The Na and the NO3 are going to combine to make a salt. And then, like I said, the carbonic acid, the H2CO3, is going to break down further and give you water and carbon dioxide. And then the salt remains unchanged, so that's still NaNO3. All right, the third example is sulfites and bisulfites. So this is a case where it would be helpful if you remember your polyatomic ions that we learned at the beginning of the year. And if you haven't, then maybe refresh yourself a little bit just to make sure that you're clear on which kinds of salts can do these reactions. So in this case, we have an acid that reacts with a sulfate salt. It could be a sulfite or a bisulfite. And you get sulfurous acid, H2SO3, and salt. All right, and then the acid breaks down further to make water and SO2 gas, and the salt remains unchanged. So in this particular example, we have HCl reacts with lithium sulfite, and you get H2SO3 as one of your products, and the other product is going to be lithium chloride, LiCl. All right, and then that's going to break down further to make H2O liquid plus SO2 gas plus the lithium chloride, LiCl. And then the final example we have here are ammonium salts. And ammonium, remember, is NH4 plus. And those are going to react with a base. So in this case, in the first three examples, we all had anions that were reacting, and that's why an acid is what they were reacting with. This is a cation, and so it's going to react with a base. So the particular example we have here is ammonium chloride reacting with potassium hydroxide. And so one of your products is going to be ammonium hydroxide, always, because those are the two components that have to be there for this type of reaction. And then a salt. In this case, the salt is KCl. And then the ammonium hydroxide breaks down further to make water and ammonia gas, NH3 gas. All right, so in this case, our final products would be H2O plus NH3 gas plus KCl. All right, now that you have a refresher on acid-base reactions, I just want to go over the terminology. So it's important to note that there are three different types or three different classifications of or definitions for acids and bases. The one we are concerned about in this class, the one we use most often, and I think the only one I told you about in honors, are the Bronsted-Lowry acids and bases. There's also an Arrhenius definition, and there's a Lewis definition, but we are not going to deal with those in this class. You might get to those in a college class in the future. All right, so a Bronsted-Lowry acid, by definition, is a proton, or H+, donor, and a Bronsted-Lowry base is a proton acceptor. Okay, so you notice that neither of these definitions has anything to do with OH-, which is frequently present in a base, but not always. So it's possible to have a base that will accept a proton, but doesn't actually contain OH-, and we'll get through some examples of those as we continue on in this unit. All right, and then the last word I want to refresh you on, and again, we covered this in honors as well, but amphoteric. And that means that it's a substance that can act as either an acid or a base. And so there are a few examples of this. The most common example is water, because water can accept a proton and become H3O plus, or it can donate a proton and become OH minus. And those are the most basic examples and the ones you'll come in contact with the most. But just some terminology. Amphoteric means it can be either an acid or a base. Okay, so that wraps up our basic introduction, and we'll get into more detail in the next lesson.